Hey Joey, I'm sending you a solution for the bacteria. This is actually a sampling distribution problem, and I thought I would show you a little. I did a hand solution here. Um, if we were to just take one sample of this milk, I mean the problem says that at a dairy, we go sample inside the tank, and if we were to just take one sample where we knew that the mean bacterial count was 2,500 and standard deviation 300, okay, um, and we wanted to know the probability of one sample being between 2350 and 2650, that would look like this. Okay, we would convert to a z-value, which you know how to do that. So we would be finding the area between negative zero point 0.5 and zero point 0.5. And I can go look that up on a z-table, or I can just do it on my calculator very quickly. And while I'm doing that, I'll just tell you, you can go to the normal CDF. In fact, let me go ahead and do that. I'll go to the calculator, and we'll say, go to sampling distributions. I can also look it up on the z-table, but of course this is quicker, and I prefer this. Okay, so we're going to put in our low value, which is 2350, and our high value is 2650. Our mean is 2500, and our standard deviation is 300. And we get about a 38% chance. So we would have a 38% chance that if I just took one sample, that there would be, a bacterial count between 2350 and 2650, right? But for sampling distributions, if we took 32 samples, and we found this out from the central limit theorem, the central limit theorem says that three things really. It says that the more you take sample means, then your distribution is also going to be normal. It actually doesn't have to be normal to begin with. It can be skewed. I put a video on the announcements there that shows that. But your sampling distribution is going to be normal. And another thing is the mean of this new sampling distribution will equal the mean over here, so that's also going to be 2500. But the standard deviation is now going to be the standard deviation of the original distribution divided by the square root of your sample size. And sometimes that's referred to as the standard error. So look what happens just by sampling more, and you would expect this to happen. All of a sudden, we have z-values when we convert it from minus 2.83 to 2.83. And if I do that on the calculator now, so let's go to the normal CDF, cumulative distribution function. And once again, my low value is 2350. My high value is 2650. The mean is 2500 still. But now my standard deviation is going to be 300 divided by the square root of 32. Oops. I need a comma there. That'll probably give me an error. Okay, and let's see what that looks like. Now I'm almost 100% confident that if, that just says that the more I sample, my probability now is 0.995. Okay. And that is so powerful. Like, we can't say much about what's going to happen individually or to any individual, but if we take lots of samples, we can say with confidence about the entire population. And that's really what statistics does for us. That's the reason I'm sending you this video, is because this is such an important concept, the central limit theorem. I hope I've done it some justice here, but you really should read up on it. And basically, the more I sample, so on this one I got 32 samples, now I can be 99.5% confident that this, milk is not contaminated with this strain of bacteria. If I had only sampled once, I could only be 38% confident, which isn't very confident when you're talking about, milk being contaminated or whatever. But having sampled 32 times, I can be 99.5% confident. Okay, so hopefully that this will help you, and I'll attach it to that. And you can resubmit the assignment, okay? All right, this is Mr. Lonnie. Bye.